Okay, so in the second part of this lecture, we are going to have a look at the UMTS air interface, and that's the wideband CDMA network. So just a quick revision. Previously we looked at GSM and GPRS, and we noted that in both in GSM as well as in GPRS, we had this idea of a carrier frequency being used, and we had to ensure that every cell had a carrier frequency which we did not use in adjacent cells. So we had a frequency reuse factor greater than 1, and again on each carrier frequency we divided it in the time domain, and we created time slots, and we allocated a time slot for the use of a user. When we move to wideband CDMA, the concept changes quite a bit. We see that in every cell we can use the same frequency. So we may use frequency F1 for the downlink transmission on one cell, and we could use the same frequency F1 in an adjacent cell. So how does it work? How is it possible that for all of the users to communicate? So all of the users share the same frequency in the time domain, but what we use is the idea of codes, and these codes have a property called orthogonality. Okay, and that is expressed by the integral on the slide. So we'll talk about orthogonality of codes a little bit later and how they're generated, but the basic idea is that all the users transmit at the same time and on the same frequency and in the same space, but each user will be allocated an orthogonal code. And just like in GSM, wideband CDMA can work in the FDD mode, so that means we separate the uplink and downlink in frequency. But there's also a possibility for wideband CDMA to work in the TDD domain, and in the TDD domain the uplink and downlink is in the same frequency band, but they are separated in time. Let's move on. Okay, so a very good example of wideband CDMA was this slide courtesy of Suresh Koyal and Richard Howard. So when you look at this diagram here, you see that there is a garbled message on the screen right now, so we do not know what it is. But if we were to apply a filter, let's just say we have two filters here. We have a pink filter and a blue filter. So let's apply the pink filter first, and you see when we apply the pink filter we see the word dog. Now let's apply the blue filter, and you see the word cat. And this is the basic idea in wideband CDMA. You see that everybody's transmission is coded with a specific orthogonal code, and as long as the transmitter and the receiver know this orthogonal code, they can decipher the message, just like we were able to decipher the message using the red filter and the blue filter. So and if we apply the wrong filter, then we will not, all we see is noise. Okay, so in just a quick recap about spectrum, which we talked about in media access control lecture, which was the third lecture. Now here we have two possibilities in spectrum. We have something called direct sequence CDMA. Okay, and the second possibility is frequency hopping CDMA. The first one is the more popular one, the direct sequence CDMA. And the basic idea is that all users use the same frequency to carry the information, and every user's transmission is separated by means of spreading codes, and these spreading codes have the property of orthogonality associated with it. And this is the technology that's used in both the FDD and TDD version of UMTS. In the frequency hopping case, what we have is the carrier frequency being changed at a very rapid rate. So it gives the impression, we have to make sure that different users are hopping with different patterns, and no two users are using the same frequency at any one time. So and this technology is also there, but it has not found commercial use. Okay, so we go back to an understanding how the multiple access scheme works here. So in the case of Intra and FDD, what we have is we need a 5 megahertz bandwidth. So if you're using the FDD version of UMTS, you need 5 megahertz bandwidth for your uplink transmission, and you need 5 megahertz transmission for your downlink. That's the minimum requirement. Okay, so some operators, especially the ones with more money with them, they may have more than one of these 5 megahertz chunks. They may have two of these carriers and so forth. So in the UMTS system as shown on this slide, we use the most popular configuration is the 1800 1900 band. So here we have frequencies between 1920 megahertz and 1980 megahertz being used on the uplink, and this bandwidth or this band of available frequencies is divided into 12 5 megahertz chunks, and each operator who intends to use a 3G network would have purchased one of these chunks, and these were mostly sold in the form of auctions, and a lot of operators paid a lot of money to get these 5 megahertz chunks. Now we move on. So now we've talked about the idea of spreading, and let's have a look at this a little bit more in detail. So the basic idea is, as you can see in this diagram here, this is the basic data that we want to transmit across the interface, and the duration of each these are referred to as symbols. So here you have one symbol, here you have a second symbol and a third symbol and a fourth symbol and so forth. Now usually a 1 is coded as a +1 and a 0 is coded as -1. So what we do is we take this the data that we want to transmit, which is essentially a narrowband signal initially, and we multiply it by a chipping sequence. So in this case you can see this data 10 is multiplied by a chipping sequence corresponding to 10 11 0010. That's the chipping sequence that we use. So when we multiply this is remember this is +1, so we have a +1 and a -1. So when we multiply this, the output you're going to get is very much similar to the chipping sequence when the data is a 1, and when the data is a -1, the output is the inverse of the chipping sequence. So this is the output that we will get as a result of multiplying the data by the chipping sequence. Now what happens at the receiver is a despreading process. So in the despreading process, what we do is we take the code and we multiply the incoming signal. Okay, one other thing that I forgot to mention is that in the process of multiplying our narrowband signal by the chipping sequence, we end up going from a narrowband signal to a wideband signal. Okay, and this is the wideband signal that is transmitted across the interface, and when it's received at the receiver, the wideband what we do to the wideband signal is we multiply it by the code again, and in the process of multiplying it by the code, we get the original data. So the important condition to receive this original data is that we must use the same chipping sequence in the transmitter as well as the receiver. Okay, so this illustrates the case when you don't use the correct spreading code at the receiver. So if you multiply the received signal by the incorrect code at the receiver, you'll still end up with your wideband signal, and that is of no use for the purpose of communication. Okay, so just to recap, in the case of multiple access in wideband CDMA, you may have two users, user A and user B. Initially, both the users have a narrowband signal, and then we multiply. In the case of user A, user A multiplies by their chipping sequence, and you go from a high power low bandwidth signal to a high bandwidth low power signal, and B does the same thing, but B uses a different code. And basically this wideband signal is transmitted across the interface, and what you receive at the receiver will be the sum of all the signals from all the users. So that's what that represents. Now at the receiver, if you multiply, if whoever user A is communicating with, if that receiver multiplies it by the code that A used, then you again go from your wideband signal to a narrowband signal, whereas the user B's transmission continues to be a high bandwidth low power signal, and that can be filtered out. Okay, so the basic idea in wideband CDMA is that we have two codes. We have something called channelization code and scrambling codes. So in the process of scrambling our data, we take our baseband data and we multiply it by the channelization code first, and then scrambling code. Now associated with channelization codes is the concept of spreading factor, and we'll talk a little bit more about this a bit later. Okay, so this diagram here gives us an idea of how these codes are generated. Okay, so now the best way to understand this is, you see we start off at the root of this code. Okay, and here we start off with 1, and what we do is we copy this number to the first part of this code. So you see a 1 has been copied here and a 1 has been copied here. Now the second bit is on this part of the tree, is exactly the same as the previous one, and on this part of the tree it is the inverse. So if you have a 1 here, it becomes -1. Okay, now we repeat the same process down the tree over here. So 1 1, so this becomes 1 1 and 1 1, and this one here is exactly a copy of this, and this part here is the inverse of this. Okay, and this is how the tree is generated, and this tree can go very deep. You can go 128 levels deep if necessary. So associated with each one of these is a spreading factor. So the codes on this one are referred to as spreading factor 1. The codes on this part of the tree are referred to as spreading factor 2. The codes on this part of the tree are spreading factor 4. The next one will be spreading factor 16, and the subsequent one will be spreading factor 32, and so forth. So now there is some rules that we need to take care of when we allocate the code trees. So you see that if I were to allocate a code like 4.2 to user, so basically what I mean by 4.2 is that it's spreading factor 4 and it's a second code, associated with spreading factor 4, and it corresponds to 1, 1, minus 1, minus 1. If you were to allocate this code to a user, all of the parents of that code cannot be allocated to any of the users, and all of the children of this code, and remember this tree can go deeper, and all of those children cannot be allocated to anyone. So this is an important point. If you were to allocate 4.2, C8.3 and C8.4 generator cannot be assigned to other users, and the parents, which corresponds to C11 and C21, cannot be allocated. So in the process of allocating this code, we are approximately taking 1/4 of the available codes cannot be used. So the basic idea is, whenever we allocate codes as down this tree as possible. Okay, the more down this tree we go, the better it is. Okay, now what is the relationship between codes and data rates? And that's given on this part of the table. Okay, so if a user is requesting a service that's 960 kilobits per second, which is a very high data rate, then we have to allocate them a code on spreading factor 4. So that's one of these 4 codes. But as I said a few minutes ago, if you were to allocate one of these codes, then 25% of the code tree will not be usable thereafter. Okay, so if a user was to request 480 megabits per second, we would allocate them a code from spreading factor 8. Now the most important thing here is that the product of the bit rate and the spreading factor is always equal to a constant of 3.84 megachips per second. So this is the chip rate associated with wideband CDMA. Okay, so 480, if a user wants 480 kilobits per second, we've got to allocate them a spreading factor of 8. So we've got to allocate them a code from here. So if you were to allocate this code, for example, then you can see that all the parents of this code cannot be used thereafter, and all the children of this node here cannot be used as well. So that means approximately 12.5% of the code tree will become unusable. Okay, so as I said earlier, we always try to allocate codes further down the tree as much as possible. Okay, so this diagram sort of tells you what's happening in terms of codes and when you have multiple users. So you can see that each you can think of this as a piece of cake with different layers on it. So and this has in the frequency axis, this has a bandwidth of 5 megahertz, which is the basic bandwidth associated with a wideband CDMA carrier. And this is the time axis. Okay, and this time axis goes in chunks of 10 milliseconds, because that's the frame length associated with wideband CDMA. So you can see that you have a blue user who is transmitting with a very small power. Okay, and you have a green user that is transmitting two slices, because maybe the green user is having 2 parallel communication, maybe a video conversation as well as an FTP session is going on from a user and the green user, so they're having 2 chunks and so forth, and the orange user has different chunks. So each one of these slices of this cake that we see here corresponds to a session of a user, and one user could be having multiple sessions. Okay, now we see that again there's also a relationship between transmit power and data rate. Okay, so and then this comes actually from the previous slide. This slide here. Okay, so when you're transmitting data at a high data rate and you're using a lower spreading factor code, you have to transmit this at a higher transmit power. Whereas if you're transmitting data at a lower data rate and you're using a very high spreading factor code, you can afford to transmit it at a lower power. So there's a relationship between power and data rate. Okay, the higher the data rate, the higher the transmit power, the lower the data rate, the higher the spreading factor, but the lower the data rate. Okay, so remember this relationship between data rate, spreading factor, and transmit power. Okay, so we'll have a look at power control. Power control is very, very important in the case of wideband CDMA. Why is it very important? Because of a concept called near-far effect, which we talked about in the lecture number 3. Okay, so let's consider the case where we have 3 users in this particular cell, and they're all transmitting to the base station. Now, this graph on the side here represents the received power from these 3 transmitters. Now, if mobile station 1 was very close to the base station, if its signal was received at very high power compared to MS2 and MS3, then you can see that there's a possibility that this signal will drown out the rest of them. A good example is, if you're sitting in a room and you are talking to a group of people and somebody comes with a loudspeaker and it starts yelling on that loudspeaker, then you won't be able to hear anybody else in the room. Okay, so what's happening there is that one person's signal is swamping the rest. Now, this is very important. This can happen quite easily in the case of wideband CDMA, because remember, everybody's transmitting at the same frequency and at the same time and in the same space. So we have to be very careful about the near-far effect problem. So what we have to do is, when we have multiple users that are transmitting within a cell, we've got to make sure that the received power from all of the users are approximately the same. And we use power control to make sure that happens. Okay, so power control is very important in wideband CDMA. It removes the near-far effect. It also removes the effect of fading, because if a user signal was to experience fading, then to compensate for that fade, we can ask the receiver, or the transmitter, to increase the transmit power so as to mitigate the effect of fading. And it can also compensate for any changes that could occur in the radio propagation conditions. Okay, so the most important thing about power control in wideband CDMA is make sure that the received signal power from different users are approximately the same when they arrive at the base station. And on the downlink direction, because whatever is transmitted on the downlink could be interference for neighboring cells, we want to make sure that we try and keep the downlink transmit power as low as possible, so as to decrease the interference to users in other cells. And this is important because in the case of wideband CDMA, every cell is using the same carrier frequency. Okay, in the case of power control, there are 3 important types of power control, and we'll study this a little bit more in detail when we get to the radio resource management class. So we have something called open loop power control, fast closed loop power control, and outer loop power control. So open loop power control is a mechanism that is used to set the initial transmit power for a mobile station across the interface. Initially, a mobile does not know what its transmission power is and what should be transmitting at, and so what it does is it goes through a process of slowly increasing its transmit power until it establishes communication with the receiver. Fast loop inner loop power control is probably one of the most important power control mechanisms that's used, and it is performed pretty at a pretty high rate. So it's performed at 1500 times a second, and it's done both on the uplink as well as the downlink, and it is to ensure that the signal quality is maintained at the optimum possible. And then you also have something called outer loop power control, which is performed here. Okay, as I said, we'll talk more about this in the radio resource management class. So in terms of handovers, what do we know about handovers? Well, in the case of wideband CDMA, there are many different types of handovers. The first type of handover is referred to as inter-system handover. So we are going from one system, which is, in this case, it could be a 2G system to a 3G, or from a 3G system to a 2G. Okay, so it's possible when you roll out your 3G network initially, it might not have nationwide coverage. So there might be areas in which you don't have 3G coverage, but you can have GSM coverage, in which case you want to do a handover from a 3G network to a 2G network. And it's also possible to have the handover from our FDD to a TDD system. That's also classified as inter-system handover. And the next type of handover that you could have is intra-system handover. So that's within the same system. So here we're talking about a handover that's occurring between two cells within the wideband CDMA FDD system, or it could also be a handover that is taking place between two cells in the wideband CDMA TDD system. Now, within the intra-system handovers, there are two possibilities. In fact, there are three possibilities. You can have soft handovers, hard handovers, and softer handovers. So let's have a look at the difference. So we'll initially look at the difference between soft and softer handovers. Okay, so when we talk about a handover that is taking place between two sectors that are in the same cell site, that is referred to as softer handovers. And when we're doing a handover between two cells, adjacent cells, that are not associated with the same base station site, then that will be a soft handover. So what happens in a softer handover? Well, in a softer handover, it's possible that a UE is located in an area where it is in an area which is in the overlap of two sectors associated with the base station. Okay, and it may be communicating with both the base stations using different scrambling codes, and there may be a need for a handover from one to the other. That's possible, but most of the time it might be communicating simultaneously to both the on both the sectors. A soft handover is a handover between two cells that are served by different base station sites, and it's also possible that these two base stations are served by different RNCs. So and the probability of this occurring is pretty high in the UMTS system. So what's happening in terms of processing? Well, as in the case of software handover, the UE is communicating with both the base stations simultaneously using different scrambling codes, and it uses a rake receiver at the receiver to separate on the downlink the transmissions it is receiving from the two base stations. Okay, so we have intra-system handovers and inter-system handovers, and within intra-system handovers we can have either soft handovers, or hard handovers. All intra-system handovers are hard handovers. Okay, so that's about it for the time being, and I'll talk to you later.